Have you ever wondered if the future of computing isn't about building bigger machines, but rather reshaping the very geometry of reality itself? We often hear that quantum computers will revolutionize everything, but the path from abstract theory to a working device in your pocket has felt like a distant dream. What if the breakthrough we've been waiting for wasn't about adding more qubits, but about changing the shape of the chip itself? Welcome to a new chapter in quantum science. Today, we are diving into a collection of groundbreaking studies that suggest we are finally crossing the bridge from theoretical supremacy to engineered practicality. You will learn how a specific type of transistor, the silicon FinFET, has overcome decades of limitations to host stable quantum bits, how the mathematics of open systems is being rewritten to account for real-world noise, and why the race for quantum artificial intelligence might look surprisingly different than we expected. Stay until the end, because the findings on single-qubit machine learning challenge the very notion of immediate quantum superiority, offering a more grounded and exciting roadmap for the future. For years, the field of quantum computing has been caught in a tension between abstract mathematical beauty and the messy reality of physical hardware. The central problem has been a bottleneck in scalability and fidelity. While we can manipulate individual atoms in a lab, scaling these systems up to solve real-world problems has been plagued by decoherence and error rates that threaten to undo our progress. Researchers have long debated whether simply adding more qubits would lead to better performance, or if the fundamental architecture of our devices was holding us back. Furthermore, there has been a disconnect between the elegant, closed-system geometries used in theory and the dissipative, open nature of real quantum systems interacting with their environment. If we cannot maintain high fidelity as we scale up, or if our mathematical tools fail to describe the noise inherent in real devices, the promise of a quantum revolution risks remaining just that, a promise unfulfilled. But now, a wave of new research is turning the tide. Imagine a standard computer chip, the kind that powers our smartphones, but redesigned in 3 dimensions. Recent simulations have confirmed that these 3D silicon FinFET structures can maximize the fidelity of whole-spin qubits to over 99%. This is a monumental shift. By moving away from flat, 2-dimensional constraints, engineers have unlocked a geometry that naturally protects quantum information. It turns out that the specific arrangement of gates in these 3D structures allows for optimal control, effectively solving the stability issues that have plagued previous attempts. Simultaneously, our understanding of quantum complexity is undergoing a profound transformation. Traditionally, the geometry of quantum states was viewed through a rigid, reversible lens. However, new work extends this view to open systems, revealing that the natural geometry governing dissipative quantum processes is not the familiar Riemannian type, but a more flexible, subfinslerian geometry. Think of it like navigating a landscape. In a closed system, you are walking on a perfectly smooth, predictable sphere. But in the real, open world, the ground is shifting. Friction is everywhere, and the shortest path between 2 points is no a straight line, but a complex curve that accounts for energy loss. This new geometric framework provides a rigorous metric for this dissipative complexity, bridging the gap between abstract optimal control theory and the actual, noisy behavior of quantum devices. Perhaps most surprisingly, when we apply these advances to the hot topic of artificial intelligence, the results defy the hype. You might expect that a quantum computer would instantly outclass classical neural networks. Yet, rigorous testing of single-qubit quantum classifiers reveals that while they can match the accuracy of classical models using clever data re-uploading techniques, they do not currently exceed them. This is not a failure. It is a crucial clarification. It tells us that the immediate future of quantum machine learning isn't about a sudden, magical leap in performance, but about establishing competitive, minimal resource models that can run efficiently alongside classical systems. The focus is shifting from seeking a quantum advantage in raw speed or accuracy to finding practical, hybrid loops where quantum and classical resources work in tandem. These discoveries collectively signal a decisive pivot for science and technology. We are moving away from the quest for abstract supremacy and toward hardware-aware optimization. The validation of 3D FinFET structures provides a concrete pathway for manufacturing scalable qubits, moving beyond the constraints of old heterostructures. For the global community, this means the integration of quantum logic into everyday infrastructure is becoming a tangible engineering challenge rather a distant theoretical puzzle. The development of parallel error correction decoding further solves the latency bottlenecks that once threatened large-scale networks, making the dream of a distributed quantum internet increasingly feasible. As we stand on this new frontier, the questions we ask are changing. Instead of wondering if quantum computers can simply do more, we are now asking how specific material parameters affect stability in these new 3D architectures, and how our new geometric frameworks can generalize to complex many-body systems. The journey is no longer about proving quantum mechanics is weird. It is about engineering that weirdness into reliable technology. In summary, today's research highlights a mature phase of quantum science, where practical engineering takes center stage. From the stability of 3D silicon chips to the new mathematics of open systems, and the really